Okay, so let's get started. So last time I started explaining a new topic, and that's basically the concept of Lie derivative, and then moving forward, we will talk about a bit of Poisson geometry or Poisson Lie groups. So we didn't really do much last time. We only defined vector field. So I'm going to just write the definition again. So remember that the vector field on the domain is just an assignment of vectors to points on that domain that vary continuously. So more precisely, here's the definition. A vector field on some open set U in Rn is just a map. And we are in a smooth world, so we want to assume as much differentiability as possible. So I say just a C infinity map, infinitely many times differentiable, like X that goes from U to Rn. So the vectors are in the same space where U belongs to, where U is an open set, okay? And the flow of this vector field X is a map which I denote by phi upper X. And with a little bit of generosity, I assume that the flow is defined for some interval of time uniformly. So I assume this flow is this map phi upper X from U cross the interval minus epsilon to epsilon to U, which is a trajectory whose velocity is given by the vector field X. So this means that at time 0 and any point P, I get P for any P in U. And at an arbitrary time, if I compute the velocity, which means if I differentiate this phi upper X with respect to T at any time, for time any T naught in the interval, where time is defined like minus epsilon to epsilon. Oops, I just got some extra window here. All right. So this is just equal to the value of the vector field at that point. Okay. So as T varies, so what you see if you start from P, as T varies, you see this curve. This is like phi upper X T of P. At any time T, you will be at some point on this path. And the derivative will describe the tangent, will be given by the tangent vector. So the tangent vector is just this X, XP. Okay, so it describes the velocity and direction of movement at that point. Well, not XP, sorry about that. This is really X of the point. So X of phi XP. Okay, all right. And well, from ODE theory, which I cannot assume you guys know, one knows that there's a unique solution to the system. If one exists, there's a unique solution, and under some conditions, there exists a solution. Okay, so we can assume that such a thing exists. Okay, and now when you have a flow, you can now differentiate your vector field, or rather differentiate functions along the vector field. Well, I mean, you can always have a flow, and so what I mean is that you can define the differentiation, partial derivatives of functions. So for any function like f from U to R, we define the derivative of the function in the direction of the vector field. This is something like a partial derivative in the direction of the vector x. Okay, But the difference is that the direction can change overall. I mean, the different points, you have different directions. Okay, so this partial derivative is just the derivative along the curve. That's the trajectory of a point when the movement is via the vector field. So more precisely, this is just d dt of f of phi tx p at t equal to 0. So maybe I should say this is lxf of p, okay? So as you see, this composition is the value of the function on this curve, on this trajectory, which is described by the flow, okay? So it's basically like a directional derivative with respect to the flow, okay? All right, and this L sub x is called the Lie derivative. Let me measure this. So the Lx. So is called the Lie derivative. Corresponding to x. Okay. How many of you are familiar with the concept of a Lie derivative? You're familiar. Yes, you have done control theory, so you've seen this concept. Okay. Anyone else has seen the derivative? Is it new to everybody else? Okay. All right. Now, the reason, maybe one reason why Lx is called a Lie derivative is that indeed it's closely related to a Lie algebra structure on vector fields, which I'm just going to describe right now. So first observation is that flows of two different vector fields do not necessarily commute, which means that so here's like maybe sort of a remark. So if you're given two vector fields, so let's say given x and y on U. So in general, if you start with a point in the domain U and first move with respect to the first vector field x in for like up to like for s seconds or like for up to time s, so you get to this x sp, and then from this point, if you like, you can continue your movement now with respect to y for like another time t. So here you end up with phi ty phi sxp. Whereas if you do it the other way around, which means first you go with respect to y for t seconds. So you go phi. So here this is phi y t p. And then you go with respect to x again, with like what this time for s seconds. So you end up with phi x s phi y p. Then there is no reason to expect that we end up in the same points. Okay, usually we don't. So in general, phi s x phi t y of p is not the same as phi t y phi s x p. Okay. So now that these two are not the same, a natural question is, if we want to measure the distance between two vector fields, maybe we can look at these flows and see how far apart they are. In other words, we want to compare the distance between these two, okay? But in general, okay, so now if I take a domain in Rn, you can use ordinary like Euclidean distance and say how far these 2 points are. However, we know that in general, we should think about domains as manifolds. In other words, we can't assume that we have this standard distance because the domains, well, we have to, or rather, we want to define all these concepts at the manifold level, which means that you have a space that's covered by these charts. And distance in two different charts can be different. So there is really no way to compare them a priori, okay? Therefore, we should come up with a way to measure the difference without referring to the distance, okay? And one way to do this is, again, to take advantage of this idea, which means that you take a function on the domain U. Now, functions on U are functions on U anyway. And that's some concept independent of the choice of the chart. So if we can assume U is a chart, like functions on U are just functions on U. And now you can compare the distance of the value of the, or rather the difference of the value of the function at these 2 points. So now, given a function f going from U to R, now we set delta of S comma T comma P to be f of the first value, which is phi S X phi Y T, phi Y T, right? Minus f of phi T Y phi S X. Okay, so now this difference in values can tell us about how distant x and y are for a given function. Okay, so that's one way to measure this without referring to a distance on U. Okay, is it plausible? It's a reasonable way. I mean, maybe it's not the best way to do this, but it's a reasonable way to do this. But some miracle happens. So now if you have a function, okay, so you have a function in like S and T, this delta of S and T. Okay, you want to see like this function, I mean, it's supposed to say like, it's supposed to stay away from 0, right? And you want to say how far it's from 0. So one way to measure this is like, you know, you look at the derivatives of a function, how fast they grow and so on, okay? Now, a miracle happens if you look at the second derivative at 0. So I'll explain this miracle to you right now. So let me just first give this lemma. And that is that if you compute the second partial derivative with respect to S and T of this delta of STP, so you fix P and you differentiate with respect to S and T and then evaluate at 0. Then what you see is the commutator in the Lie sense of the operators Lx and Ly. Okay, so now you see here I have x and then y and y then x, and so here I got the yx and then xy. So sometimes you see a definition of the Lie derivative with a minus sign to fix this, but okay, then you might want to ask why you put the minus sign there. But anyway, so maybe that's really the reason to make the like get the sort of a bracket in the right way. But anyway, it's a correct lemma this way, and the argument is very simple. So how do we prove this lemma? This is just calculus. So let us differentiate each of these terms with respect to S and T and then subtract. Okay, so let's differentiate the first one. So first I do d ds of f phi xs phi yt. So now t is fixed and I'm differentiating with respect to s, so I can assume this point is fixed. So what I see is that I'm differentiating f of phi s at some point, and that's just the Lie derivative, right? So this is by the definition of the Lie derivative. This is Lx f at the point phi dyp. Note that I'm differentiating at s equal to 0. And now I have to differentiate the right-hand side one more time, this time with respect to t. So if I set g to be this Lxf, this function for any point, so then the derivative with respect to t of this Lxf of phi t y p, it is just L, well, it's just the partial, maybe I should write it as like d dt of g phi yt p. And note that I'm doing this at 0, right? So what I see on the right-hand side again is just the Lie derivative with respect to y of g. Just look at this formula. Just look at the definition. Replacing f by g and x by y, I get this last. So the right-hand side is just Ly of G at P, which is then Ly Lx F at P by the definition of G. Okay? And if I do the same process with the other term, with this one, I get the Lx Ly. All right? Is it clear? Right, so consequently, so now, a similar argument, so maybe I just say similar reasoning. Yields d squared ds dt of the other term, which is f of phi yt phi xs p is lx lyf at p. Okay? And taking the difference, what we obtain is that d squared ds dt at s equals t equals 0 of delta stp is LYLX of F at P minus LX LY of F at P. Okay, and this completes the argument. Okay, so the second derivative gives you the commutator of these two operators, LX and LY. So you're already getting close to Lie algebras, right? Now, more interestingly, even though I did second derivatives here, this commutator really is a vector field. It's given by some LZ. In other words, it's an order 1 differential operator. Remember that the vector field basically describes some operator which does partial differentiation only once in different directions. So if I do Lx Ly, technically I am doing partial like I'm doing like a d squared over dx1 dx2 or something. But if I take this difference, somehow magically all these order 2 terms cancel out and you get an order 1 thing. And that's the next lemma. All right, so the next lemma is the following. So for vector fields x and y on U, we have Lx Ly minus Ly Lx as an operator on functions equals Lz for some vector field Z. Okay, and in fact, we can compute that vector field in terms of x and y. So how do we see this? Well, we can just express x and y in coordinates. So what is a vector field? So x of p, so this domain U, it's some domain in Rn. And Rn has this standard basis, the EI. So E1 to En. Let me specify this. So let E1 to En be the standard basis of Rn. So what this means is that EI is the vector whose ith coordinate is 1, all other entries are 0. Is this clear? Everybody happy? Okay. So then we can express both x and y in terms of this basis. In other words, each of the EIs can be thought of as a constant vector field. It's always pointing in the direction of EI. And so xp for every p can be written as a sum sigma AI p EI And yp also can be written as sigma BIP pi. Okay? So at each point, you can, like any point P in U, you can look at this vector XP and write it as a linear combination of the standard basis. You get these coefficients, which are smooth functions of P with real values. Okay? And now you can see the lead derivative has a simple formula in coordinates. So if you do Lx f, so what is this exactly? So let's look at this formula again. So this Lxf really is the derivative of a composition. You compose two functions. Now, from calculus, you know the derivative of a composition is composition of the derivatives, but this time as linear transformations. So you have to differentiate f, and you have to compute the derivative of the flow, but the derivative of the flow is just the vector x. All right? And the derivative of f is a function from some domain in Rn to R, so it's a derivative. So it's df. From calculus, you know, it is really d dx1, df dx1, df dxn. Yeah? It's not showing again? Oh. Did you run into the same issue like last time? Okay, so it's just Zoom that is frozen, it seems. Is it just this browser that's okay? The browser. Why is it not showing it? Maybe I should stop share and share again. Okay, now it's showing. Okay, for some reason. All right. Okay, so the derivative is just this vector. It's the gradient, right? All right. And well, now you have to compose this derivative by the derivative of this flow, but the derivative of the flow is just the vector x. So you have to just multiply the column vector from x with this row vectors. What's that column vector? This is a1p up to anp, because you wrote this vector in coordinates. That's what you saw. And so when you multiply, you see sigma aip d dxif. So this is just sigma aip df dxi. Okay? So I'm doing calculus again, right? And same thing happens for Ly. So Lyf is at any p, it is sigma BIP df dxi. All right. So now remember, I have to compute this composition, Lx Ly minus Ly Lx. So let's compute Lx Ly and see what happens. So if I do Lx Lyf at p, so I have to compute Lx of what I have here, which is sigma BIP df dxi. But this I know how to compute. This is like, well, we have a formula for Lxf as well. So this is sigma d dx. So maybe I should write the aj. Forgot the aj. So I have this a jp d dxj of this BIP df dxi. Okay, but I have now a summation over both I and j. All right. And now what's the last step? So now I have d dxi of a product of two things. Here I use the Leibniz rule, right? So I can write this as sigma a jp dbi dxj of p times df dxi of p plus sigma ajp bip d squared f dxj dxi. Okay? So this is both like for I and j between 1 and n. So far, I got something that's consistent with what I said. Lx, Ly, it's a composition of two operators which are order 1, which means each of them will do one partial at a time, like partial ddxi. But now, when I compose them, I got second order derivatives. But the good thing is that if I do Ly, Lx, this term is the same in both Lx, Ly, and Ly, Lx. So it cancels out. Okay? By a similar calculation, so we obtain that this term minus the one with roles of A and B switched. So you get this sigma AI okay. By the way, I wanted to, okay, did I want to compute LXLY or LYLX? Okay, LXLY, so then, okay, so now I have to do AAs. In the notes, I did the LYLX because the previous lemma was about LYLX. So here I have to be careful about what I write. So this is like AI P D AJ DXI P minus A minus B IP the AJ. I think here is a B. Okay. So here I had a B. Okay, just like above. I switched the role of I and J. Both multiplied by df dxj. Okay. So now you see that this is a function only determined by x and y, by the coordinates of x and y. And I only have order 1 partials. Like I said, these terms, they cancel out in difference. Okay. So I can even describe that vector field Z explicitly. The vector field Z, in other words, Lx, Ly minus Ly, Lx is Lz for the vector field whose coordinates are these functions. So this is like sigma AI d bj dxi minus bi d aj dxi at p times ei. Okay. Any questions so far? So we just showed that the commutator of the lead derivatives for two vector fields is another lead derivative for another vector field. Okay. So now I can just declare that the commutator of two vector fields x and y is this vector field z. All right. And this will produce a Lie algebra structure now. So here's the next proposition. So set. So I use this fancy XU to be the vector space of all vector fields on U. Now, this XU is a vector space. Maybe I should emphasize. So what does it mean? Well, it means that, well, I mean, I can add vector fields and I can dilate vector fields by scalars. If I have a vector field X and another one Y, their sum at any point P will be just the vector field whose vector at P is just the sum of XP and YP. And dilation is you just dilate all vectors of the vector field by the same scalar. Okay? So this is a large vector space. It's not finite dimensional or anything. It's really large. Okay? But we just noticed that if we define the bracket of xy equal to z for x, y, and z as in the previous lemma, then this bracket equips xu with the Lie algebra structure. Okay, so we just created a Lie algebra out of all the vector fields on a domain U. I just want to emphasize that all of these things can be done over any manifold. So you can compose these operators on spaces of functions on manifolds, or functions defined locally on a manifold, because locally a manifold is just like a domain U in Rn. And therefore, the same proposition holds if I replace U by some manifold or some open subset in a manifold. So everything really extends to manifold theory. Yeah. The dimension of what? No, XU, the dimension of XU as a vector space is huge, because really at any point, you have an n-dimensional vector space choices. So the dimension of XU really is infinite. It's really uncountable dimensional. It's like the space of functions. The space of functions on a domain, okay, all functions on Rn, R-valued functions. I mean, there's like the space of functions F from Rn to R. There are so many functions. Okay, so this is a vector space, but its dimension is infinite. So it's not really a good idea to think about the dimension of this space, because that's really a pathological thing. It's really not so interesting, at least in what we are discussing. Any questions so far? Okay, so now here is one natural way to get vector fields. How do you get vector fields on some domain? You can get vector fields from the derivative of a function. As you saw, if we start with the function, so here is now some observation. If F is a map from U to R, and U is in Rn, you can consider the derivative, which is just this gradient. It's just like a bunch of vectors, right? So I want to put this in quotation mark. So you get like a vector field, but this is really not right. This is not the right way to think about it. And can you explain why? I got a vector field this way on my domain in Rn, but this is not right. This is not the correct way to think about it. Can you explain why? Yeah, this is a subtle point. Not too subtle, but I mean, there's something here that's worthwhile understanding. So what is the derivative of a function? So the derivative, so df, it's supposed to, if you think about tangent spaces, the derivative is supposed to be a linear transformation from some space to some space, okay? So that space, what is that space? So it will be the tangent space at the point P to U, and the values will be in the tangent space at f of p to r, which is just, R is a vector space, so this is just R. In other words, this derivative really is in the dual of the tangent space. Okay, it's a linear map on the tangent space. So this means that this assignment, the gradient, it is not a canonical assignment, or in other words, a canonical way of obtaining a vector field. What we want as a vector field is vectors in the tangent space. So a vector field should have the property that is xp is in the tangent space, okay, at any point. But we got vectors in the dual. Therefore, in order to construct a genuine vector field that works nicely with all the functorial things in calculus, which means all these compositions of derivatives and all the rules of calculus, in order to construct the right thing, we should somehow choose some isomorphism between this space and its dual space. And we know that such an isomorphism is not canonical. You can always pick a basis and in the two spaces and correspond to each other, but there's like a vector space and its dual, even though they're isomorphic, this isomorphism is not canonical in any sense. So we know if you take a vector space, the dual of the dual is isomorphic to V in a canonical way, but the dual is not. Okay. Okay. Can anybody describe the isomorphism, the canonical isomorphism for a finite dimensional vector space between V and V double star, the dual of the dual? Some of you should know this. Yeah? Can you? Pardon? Okay, so the main point is not to use a basis, because if I was allowed to use a basis, then V and V star, I could choose basis and say, okay. But I mean, when I say canonical isomorphism, it should be one that doesn't make any reference to bases. Because if once you pick a basis, you have already created too many choices. Pardon? Point evaluation, right. So you take a vector here. Now you should correspond to this some linear function on V star. You should attach to this V without any reference to bases a linear function of phi V from V star to R, because it should be in V star star. It should be in the dual of V star. So given some lambda in V star, what should be phi V of lambda? Lambda V, that's right. And as you see, I got this map now from V to V double star, taking V to this phi V, which is defined as such. And it didn't make any reference to any basis. And you can show that for V finite dimensional, this is always an isomorphism. Okay? Is it good? But you cannot do anything like this for V and V star. Okay. Actually, now I wonder if there's a theorem. Maybe there should be a theorem somewhere. I mean, some mathematical theorem that you cannot construct. I mean, something in the realm of model theory or logic, maybe that proves that you cannot really give such a construction. Does anybody know if there is some mathematically sort of rigorous? Because we know that such thing is impossible, but we have never proved it. But maybe there is such a proof. Does anybody know that? Yeah.
Actually, V is finite dimensional. V is isomorphic to V star.
Of course it is, but like I said, the only isomorphisms you can get are by choosing a basis here and a basis here and making them correspond to each other. You cannot give some isomorphism like the one I said, which without any choice of basis gives you the isomorphism. The previous isomorphism really is a unique isomorphism between V and V double star, in the sense that it works for any vector space V without any reference to any choices. Okay? And such a thing is not possible for V and V star. Okay? If you play with it, you see it's really not possible. But I mean, there should be some kind of proof, I guess. Pardon? The claim is that there is a canonical isomorphism between V and V double star. one that doesn't make a reference to any basis, any choice of basis. But you cannot do this for isomorphism between V and V star. The only way to do this is say, okay, they have the same dimension, which means you have picked the basis and choose such an isomorphism. Anyway, so this we are sort of going far astray a bit. The main point is that the derivative gives vectors, but those vectors are really in the dual of the tangent space. So we have to really bring them back to the tangent space. And well, that means that we have to pick some isomorphism between V and V star. And as we know, it's not canonical, but if you add extra structure, you can get such canonical isomorphisms. So one way would be that you assume that you have some bilinear form, a non-degenerate bilinear form on V. So here is a remark. So if omega is a non-degenerate bilinear form on V, then we obtain an isomorphism maybe I call it tau omega, again, without any reference to bases. And how does that work? So tau omega of V, it is this linear functional that maps a vector to omega paired with V. So maybe I write it more explicitly. So this is the linear functional that maps any W to omega of WV. Okay. Okay, so now I want to use this to now obtain or rather like construct vector fields from functions on U and then see what would be the meaning of the Lie bracket when I pass two functions. Okay, so to do so, I will use a specific example of a bilinear form, and that you have seen already. It's called the symplectic form, which is a non-degenerate skew-symmetric form. So we pick a symplectic form omega on Rn. Okay, so this means that we assume. Okay, maybe I should. Okay, maybe I should first pick n, and note that this implies that n is even. We do not have a non-degenerate bilinear form on an odd-dimensional vector space. Okay. And so what is this omega? So this is so the symplectic form means that omega is non-degenerate. So omega x Rn equal to 0 implies that x is 0. And the second is that omega xy is minus omega yx. Okay, so as I know that n is even, I'm going to replace n by 2n. Okay, like the dimension is like 2 times some n, some other integer n. Okay, so now here's the process. So I can now dualize the tangent vectors, or rather dualize the derivatives of functions via omega, and then those will be vector field. Okay, so now starting again, so U is some domain in Rn, R2n. So now take some H. Again, freezing. Okay. How did I fix it last time? I guess I just stopped sharing. Oops. Stop share. Share again. Okay, all right. So you take any smooth function. Real value, okay? And remember that we have fixed some symplectic form on Rn, R2n, okay? So here I should maybe add, so I mean, I didn't say this specifically. Okay, I said it here. It's like bilinear, okay? These were not in the bullet conditions, but I already said there it's bilinear. Don't forget it's a bilinear form, okay? So we fix some symplectic form, say omega. And now xp is defined by omega of whatever vector comma xp is the derivative in the direction of x. Maybe I just write it as the direction xp here. Maybe I just write it first like this, which means the same thing as the directional derivative of h at point p. Okay, you can either think about it as a partial derivative in the direction of xp or as computing the derivative and, you know, evaluating at xp, composing, you know, with the like this linear transformation, evaluating at xp linear function. Okay. All right. So it's just this partial derivative. Okay. Did I miss something here? I think I did not say this correctly. Let me just see. Not xp, sorry, I shouldn't be putting xp here. I should just put the unknown thing. Okay. Okay, so this guy. So so in other words, from xp, I obtain or rather from DHP, I obtain the following XP, the vector that I can plug in so that evaluation of the derivative at the vector is the same as omega of the vector comma XP, pairing with XP. Just this duality, okay? It's the duality that I explained about. All right. So to be more precise, or maybe more clear, I want to say that this is really in the tangent space at P to the U, which is Rn. And this guy, as we noted, this is in the tangent space star, which is the dual of Rn. So I can evaluate it on vectors in Rn, and now here, omega allows me to define xp, the vector in Rn for which this linear functional is the same as the linear function on the other side. Okay, any questions so far? Is it clear? All is good? Now, all right. So now, why am I doing this with respect to a symplectic form? The reason comes from classical mechanics. So it is possible to formulate classical mechanics in terms of a Hamiltonian function, which basically describes conservation of energy in the system. So this is called Hamiltonian mechanics. And when you write these equations, you see that everything is happening in some manifold with the property that at any point, the tangent space is naturally equipped with this symplectic bilinear form. I just simplified everything to the case of a domain. So you just see the same symplectic form attached everywhere. But that symplectic form can change, actually. And more generally, one can have a symplectic manifold with a Hamiltonian function and so on. And then this would be the general framework of formulating a problem in Hamiltonian mechanics. But I'm not going to go in that direction of describing Hamiltonian mechanics. I just want to look at this simplified situation and obtain some commutator on functions coming from vector fields now. But the motivation for this is really coming from mathematical physics. Okay. All right, so let's continue. So as I said, we now define this xp as the sort of dual to this dhp. And now here are some properties that I don't want to prove, but it's they're interesting in relation to what we just did. So so the first thing is that the flow that's associated to this vector field, it preserves omega. So what does it mean? It means that for any time in the interval where the flow is defined, if I set st0 to be the derivative of this flow, this time this is the derivative. I fixed t0, so this time it's the derivative with respect to the p variable. Okay, so then this will give me some linear transformation from Rn to Rn, and the flow is reversible, and that means that the derivative is an invertible linear transformation. And then one can see that this linear transformation Ts naught satisfies the following relation: omega of st naught v st naught w equals omega of vw for. So here I should have actually 2n because everything is happening in 2n dimensions. So this is for v and w in 2n. So what does it mean about the derivative? Where does it come from? This st naught. Where does it come from? You've seen this earlier in the course, much earlier. I mean, this should remind you of a Lie group now, which we have studied. And it was in one assignment also. I mean, remember this omega, as I said, it's a symplectic form. It's an, I mean, the group of isometries of that we call the symplectic group, and it was a Lie group, which we looked at in some depth earlier on in the course, right? Okay. So this basically says the flow comes from the symplectic group. Okay. So in other words, sometimes the operators in the flow are called symplectomorphisms. They're diffeomorphisms. The flow gives a family of diffeomorphisms, like at the formation of the space, which with the property that it preserves this symplectic form. Okay. All right. So now here's the next proposition. So remember where we started. So we started with this Lie derivative, and we got this Lie algebra structure on the vector fields. Okay, we defined a commutator for two vector fields, and the result was another vector field, and this gave us a Lie algebra there. Now, the second thing we did was for functions on U, and if we had U equipped with this bilinear form, the symplectic form, then we could construct these vector fields. Okay. So now we can pull back the Lie bracket on the vector fields and see what it gives on the space of functions, right? So here is the proposition. So the map or rather, maybe I should say, suppose maybe t going from C infinity to U to the vector fields on U is the map described above. Which is that how of H is this vector field associated to that? okay, in this process. So then, well, as I said, now you have this Lie bracket, and now you can see what would be the operation on the functions, which corresponds to this Lie bracket. That should give another Lie bracket on functions. So let's explore this and see what it is. So maybe I should say here, recall U and omega are as above. U is in an R2N, and omega is a symplectic form. It's non-degenerate, skew-symmetric bilinear form. Okay. So then, if we choose a basis like E1, En, F1, Fn for R2N, such that omega of EI, EJ is 0, and omega of Fi, Fj is also 0, and omega of Ei, Fj is delta Ij, which means it is 1 if I and j are equal and 0 otherwise, and you can always do that. Okay, the choice of such a basis is not unique, but you can always do that. So then, oops, I got too many redundant things here. I think I have to. Is there an eraser? Yeah, there's an eraser. Okay. Okay. All right. So we can continue, I guess. Right. Right. So now, if we choose such a basis, then the pullback of the Lie bracket on the vector fields is the following bracket. On the space of functions on you. So the bracket is the following. So I write this now as a curly bracket, and I'll tell you why later on. So for H and K, it's the infinity of U. This will be sigma I from 1 to N dH dxi dk dxn plus I minus dk dxi dh dxn plus I. Okay, so in other words, if I want to evaluate at P, I should do all of these at P. Okay, so the formula is not that bad. It's just some second order sort of operation. And the remarkable thing about it is that as the bracket on XU was a Lie bracket, this formula describes a Lie algebra structure on the functions. Okay, so consequence. the operation which is this curly bracket, is a Lie algebra structure or a Lie algebra bracket on the space of functions. So note that if I take two functions, I could not just do x like fg minus gf, because that would just be zero. That would not be an interesting bracket. But this is now an interesting non-trivial bracket, and it connects to this concept of Lie derivative in this fashion. Why are ideas coming from symplectic geometry? Okay. And this bracket has a name. This is called the Poisson bracket of functions, right? Now, I gave you an example where I chose the domain and the standard like basis for the symplectic form and everything, and I obtained this nice formula. But in general, the formula might look more complicated. However, this kind of bracket can be characterized by some properties, which is the purpose of the next definition. So here's the next definition. So let U be in R2N. Yeah, well, I mean, we can assume Rn for now. We don't have to specify it anymore. A Poisson bracket on U is an R linear bracket. It's an R bilinear map on C infinity of U with values in C infinity of U such that first, so the first two conditions are the conditions of a Lie bracket. So F1, F2 equals minus F2, F1. The antisymmetry, and F1, F2, F3 plus F2, F3, F1 plus F3, F1, F2 is 0, the Jacobi identity. But there is one extra property, and that extra property is inherited, or rather, it's satisfied by this specific bracket, and it becomes one of the important features of this type of bracket, and that is the Leibniz rule, which is that if I have F1, F2, F3, this is equal to F1 multiplied by F2, F3. This multiplication is the usual multiplication of functions, pointwise. Plus F2, F1, F3. So I can pick one of the two, multiply by the result of the Poisson bracket of the other two, and then add the result. So this is the Leibniz rule. And this is the Jacobi identity. And this is called the Poisson bracket. So you see the name of three famous mathematicians in one definition. Okay, so this should be significant. All right, so, okay, we have just a little bit more time. All right, any questions so far? So an example of such a bracket would be what we just saw, this formula. So this formula satisfies the Leibniz condition. And that's just calculus. Checking that this Leibniz holds is just because the Leibniz rule holds for PDXI. Okay? Is it clear? Everybody happy? So we are basically doing calculus in a fancy way. But nobody said calculus is easy. All right, should we continue? Now, here is another way to get a Poisson bracket. So you just saw, so okay, maybe I should say one example. So example, an example one, example of, the bracket. Maybe I just write this formula explicitly. So this is df dxi dg dxn plus I minus d f dxn plus I dg dxi from the above example. From the above calculations. That was not an example. I mean, from the above calculations. Okay. Now, given two Poisson brackets on two different domains, you can get a new Poisson bracket on the Cartesian product. And that's really not difficult. It's just some standard construction. So here's another example. If U and V are equipped with Poisson brackets, then U cross V has a Poisson bracket defined by the following formula, which is that for F1 and F2 functions on U cross V, I'm sorry, so we set F1, the bracket of F1, F2. So this should be a function on U cross V again, right? So you should evaluate this function at some point UV. What should be its value? So its value is the sum of the values of two Poisson brackets. One coming from the one on U when you fix the V parameter. So which means you do this bracket F as a function of only the U, because you have like two parameters. You can fix the second one and let the first one vary. You think of it as a function on U. And now you can do this Poisson bracket. And you can do the same thing with the other coordinate. So what, I mean, where do you evaluate the first one? You have a function on U, so you evaluate this Poisson bracket at U. And now you can play the same game with the second coordinate, which means you look at F1, U, whatever, F2, U, whatever. Now as a function of V, I can do the Poisson bracket on V and evaluate at V. And this, you can see that this curly bracket satisfies those three conditions. It's bilinear and satisfies those three conditions. Okay, so now next time I would like to talk about the following important example, that if you have any Lie algebra over R, you can look at its dual just as a vector space. And we can consider functions on the dual of the Lie algebra. And there is some natural Poisson bracket associated to the functions on the dual of the Lie algebra. So I'll explain what this is. And this allows you to relate the Poisson bracket to a concept in algebra called a Lie bialgebra. Okay, so I guess I'll talk about this on Monday. Are there any questions?